Hello everyone and thank you for joining our presentation today. My name is George Yasemis and I'm excited to share our work on Deep Cardiac MRI Reconstruction with ADMM, which was conducted as part of the Cardiac MRI Reconstruction Challenge 2023 at the AI for Oncology group of the Netherlands Cancer Institute and the University of Amsterdam. This is a joint work with Nikita Moryakov, Yen-Jakob Sonk, and Jonas Tuwen. Let's take a moment to outline what you can expect in this presentation. First, we will dive into the problem formulation, where we'll explore the mathematical foundations that led us to the alternate direction method of multipliers, or ADMM for short. Next, we'll discuss the deep learning framework we employed, followed by a look at the training techniques we used to optimize our models. Finally, we'll present the results of our experiments and discuss their implications. Let's begin with how we formulated the cardiac MRI reconstruction problem. Before we get into the details of our formulation, let's take a look at the challenge dataset. Provided measurements comprised two types of scans, Cine, which included short and long axis views, and multi-contrast scans consisting of T1 and T2 weighted MRI data. Moreover, these data comprised dynamic acquisitions, incorporating three-dimensional spatial information with time. In addition to its 4D nature, all data came from a multi-coil setup with 10 compressed receiver coils. Here, you can see a visual representation of zero-filled reconstructions of 3 different slices from a Cine sample in the validation set. Given the nature of the data, we formulated the reconstruction problem in 2 distinct ways. Our first approach was 2D reconstruction, where we aimed to solve for each 2-dimensional slice or phase of multi-coil K-space data individually. In addition to the 2D reconstruction approach, we introduced the concept of 2D dynamic reconstruction. This approach aimed to simultaneously solve for all phases, combining both spatial and temporal dimensions. Recovering a 2-dimensional image from undersampled multi-coil K-space measurements can be formulated as a regularized least squares optimization problem. This problem combines a data consistency term and a regularization term. The data consistency term ensures that our reconstructed images align with the acquired data, while the regularization term adds an element of prior knowledge to guide the reconstruction process. In the 2D dynamic reconstruction setting, we tackle a similar optimization problem with the difference that we aim to reconstruct not just a single image but an entire sequence of images over different time frames. One critical assumption here is that information across time frames within the same slice can be effectively shared. The choice of the regularization functional aims to enforce this assumption. By sharing information across time frames, this approach can leverage temporal correlations, potentially improving reconstruction quality. To solve these problems, we've applied 2 well-known mathematical optimization methods. We've combined the half-quadratic variable splitting method with the alternate direction method of multipliers. The ADMM algorithm unrolls the optimization process into several iterations, each comprising of 3 core updates. First, a denoising step is performed on the auxiliary variable introduced by the half-quadratic variable splitting method. Next, a data consistency step is applied on the target image. And lastly, a multiplier step which updates the Lagrange multipliers of ADMM. It's important to note that lambda is a positive penalty parameter. These 3 equations form the foundation of the deep learning module we will be employing. Up to this point, we've defined our reconstruction challenge as minimization problems within dynamic and non-dynamic frameworks. We've then reconfigured each of these frameworks using the half-quadratic variable splitting and ADMM techniques. Now, let's explore how we harness the power of deep learning within these frameworks. An important component of our approach is the sensitivity map prediction, considering the use of multi-coil data. We obtain an initial estimate of the sensitivity maps from the autocalibration signal or center of the K-space. Afterwards, we employ a 2-dimensional U-net to enhance and refine these initial sensitivity map approximations. Crucially, the sensitivity map refinement module is trained end-to-end in conjunction with the reconstruction model. In our deep learning framework, we've integrated the variable splitting half-quadratic ADMM algorithm for reconstruction of inverse problems, or V-sharp for brevity. The objective of V-sharp is to iteratively solve the ADMM formulation we've discussed in previous slides within T iterations. For each step in V-sharp, we employ distinct deep learning-based models as image denoisers, dedicated to solving the denoising step. In our work, we effectively used the UNet architecture for this purpose. To be more precise, we utilized 2D UNets for the 2D reconstruction and 3D UNets for 2D dynamic reconstruction. Secondly, V-Sharp addresses the data consistency step through a differentiable gradient descent scheme, which unfolds iteratively over multiple steps. Lastly, the multiplier step is straightforward to compute, as it updates the Lagrange multipliers directly. A critical element in ADMM success lies in the smart initialization of its optimization variables. In our framework, we initialize the auxiliary variable and image, using a sense reconstruction, incorporating the predicted coil sensitivity maps. Additionally, the Lagrange multipliers variable is initialized using a deep learning-based initializer constructed with replication padding modules and dilated convolutional networks. This model takes the initialized image as input. With all these components in place, this is how our deep learning approach operates to reconstruct the undersampled measurements. First, using the undersampled measurements, we make initial estimates for the sensitivity maps. Next, utilizing these undersampled measurements and sensitivity maps, we initialize the values for the image and auxiliary variable. The Lagrange multiplier initializer network then generates an initialization for the Lagrange multipliers, using this initial approximation. The three initializations are subsequently fed into the first UNet model, which performs the initial denoising step in the unrolled ADMM algorithm. The image then undergoes optimization through a gradient descent algorithm update for the data consistency step. At the conclusion of the first ADMM iteration, the initial update of the Lagrange multipliers takes place. This process spans T iterations, with V-Sharp iteratively refining each variable in every iteration. Our reconstruction network ultimately produces either a single image in the case of 2D reconstruction or a sequence of temporal images in the case of 2D dynamic reconstruction. Now that we've established our deep learning framework, let's explore the various techniques we've employed to further enhance the performance of our models. We'll start by discussing the first technique. For our deep learning-based approach, we employed a joint modality training. This method involved training our models using all data at our disposal provided by the challenge, including both Cine and multi-contrast MRI data. The benefits of this approach were twofold. Firstly, it allowed us to use a larger dataset, promoting more effective learning and generalization. Secondly, by integrating these data, we aimed to leverage the possible complementarity between these modalities. This approach enabled the model to exploit shared features and correlations, potentially improving reconstruction quality for both modalities at inference. Another technique we employed to optimize computational efficiency during training was random k-space cropping. Here's how that worked. Of course, direct cropping of the k-space would be inappropriate as it would distort reconstructed images. So, we first applied the inverse fast Fourier transform to reconstruct the fully sampled k-space into fully sampled multi-coil images. After the reconstruction, we performed random cropping on these images. The resulting cropped image was then transformed back to the k-space domain via fast Fourier transform. The cropped k-space data was then undersampled and downstream used as input to our models. This approach not only offered computational benefits but also allowed our model to gain exposure to different parts of the reconstructed data, including background noise and regions of interest, without compromising overall reconstruction quality. Target data were undersampled using an equispaced rectilinear pattern on the Cartesian grid. All data included a fully sampled center region with 24 autocalibration lines, and acceleration factors of 4, 8, and 10. Inspired by previous work, we employed a multi-scheme undersampling setup during training. Alongside the provided Cartesian equispaced rectilinear undersampling pattern, we employed several other undersampling schemes, as shown in the image. These schemes included undersampling patterns generated on the Cartesian grid, such as random rectilinear, variable density two-dimensional Gaussian, pseudo-radial, and pseudo-spiral schemes. Additionally, the acceleration factor was chosen randomly between 4 and 10, to match the acceleration factors of the target data. The final training technique we employed was the dual domain loss. To train our models effectively, we designed a loss function that operated in both the image and frequency domains. The image domain loss was computed between the ground truth root sum of squares image and the magnitude of the model predicted image. This loss combines several components, including the structural similarity index measure loss, the mean absolute error or L1 loss, and the high-frequency error norm. Furthermore, for dynamic reconstruction experiments, we incorporated the 3D structural similarity index measure loss, which computes the SSM metric for volumes. All other loss components computed the loss on 2D slices of reconstructed data. In the frequency domain, the loss is computed between the ground truth multi-coil K-space data and the K-space transformation of the model predicted image. The frequency domain loss comprised by the normalized mean absolute error loss and was scaled by a factor of 3, so that the contribution to the total loss matched that of the image domain loss. Now that we've covered our deep learning framework and training techniques used, let's dive into our experimental setup. We implemented our models using PyTorch and we used the ADAM optimizer with a decaying learning rate scheduler to optimize our model parameters. Our experiments were powered by NVIDIA A180GB GPUs using a batch size of 1 for dynamic tasks and 2 for non-dynamic tasks. Our pipeline tools and implementations were facilitated by our open-source MRI research code base, namely the Deep Image Reconstruction Toolkit, or DIRECT for short software. Let's take a closer look at the implementation of our proposed methods. Our first experimental setup focused on 2D reconstruction. Our goal here was to solve for each slice or time frame of 2D data independently. Hence, as a reconstruction network we employed a 2D V-sharp model using 16 ADMM optimization steps. We also exploited 2D UNets with 4 scales as denoisers, each featuring 32 filters in the initial scale and performed 14 gradient descent steps for data consistency. Using these hyperparameters, the total number of trainable parameters amounted to 125 million. Moving on to our second setup, we approached the problem dynamically. Our model in this case took as input a sequential series of time frames with 2D undersampled multi-coil K-space data, and our objective was to generate a corresponding sequential series of time frame images as the output. To accommodate GPU memory constraints, we limited the optimization steps to 10 using 3-dimensional UNets for the denoising step and conducted 8 gradient descent iterations for data consistency. With this choice of hyperparameters, the total number of trainable parameters amounted to around 100 million more than the non-dynamic setup. For the sensitivity model, for both setups, we utilized a 2D UNet with 4 scales and 32 filters for the first scale, which contained around 8 million parameters. To evaluate our methods, we compared them against 2 state-of-the-art 2D accelerated MRI reconstruction approaches, the recurrent variational network and the end-to-end variational network. Both of these approaches were trained using the same training settings, optimization, and training techniques as our proposed methods, as well as an identical sensitivity map prediction module. Now, let's dive into the results. In the table, we provide an overview of the reconstruction evaluation results on the validation dataset provided by the challenge evaluation tool. As you can see in the table, both 2D reconstruction and 2D dynamic reconstruction with V-sharp yielded superior results in terms of quantitative metrics, surpassing both the recurrent VARNet and the E2 eVARNet. Notably, as expected, the 2D dynamic reconstruction setup outperforms the 2D reconstruction for both Cine and multi-contrast tasks. Now, let's take a closer look at some reconstructions from the validation dataset. Here, we examine a T1 weighted sample with an acceleration factor of 4. As you can see, all methods show significant improvements over the zero-filled reconstructions. While the absence of a ground truth makes it challenging to identify all artifacts, upon closer inspection of the zoomed-in regions, we observe that both of our proposed methods produce reconstructions of higher fidelity compared to the baseline methods. Continuing our evaluation, let's shift our focus to a Cine short-axis sample from the validation dataset, this time with a higher acceleration factor of 10. Similar to the previous scenario, both the baseline and our proposed methods show substantial improvements over the zero-filled reconstructions. However, a closer examination of the reconstructions reveals that both of our methods exhibit fewer noticeable artifacts. Lastly, we present the time required for volume reconstruction in seconds across the 2 experimental setups proposed in our work. Although for T2 weighted MRI both methods require around 2 to 3 seconds for reconstruction, for the cases of Cine and T1 weighted imaging, it's evident that the 2D dynamic reconstruction setup requires way less inference time. This can be attributed to the fact that the 2D reconstruction process involves loading individual slices or time frames into memory and subsequently performing a forward pass through the model. Conversely, in the 2D dynamic reconstruction setup, sequences of data are loaded collectively and processed in a single forward pass through the 2D dynamic model, resulting in significantly reduced reconstruction times. Thank you for your attention. I hope you enjoyed this presentation and found it informative. If you have any questions or would like to connect, please feel free to reach out to us online and also access our code repository by scanning the QR codes.